Nitrogen. Diatomic nitrogen, N2, comprises 78% by volume of Earth's atmosphere. It occurs to a small extent in Earth's crust as nitrates, as Chile saltpeter, sodium nitrate, and saltpeter, potassium nitrate. It has a very high electronegativity next to that of fluorine and oxygen. It forms a variety of compounds in all oxidation states, ranging from -3 to +5. Nitrogen is important for life processes as it is a constituent of plant and animal proteins. Assimilation of atmospheric nitrogen by plants occurs through natural and artificial fixation of nitrogen. Preparation of nitrogen. Industrial preparation via liquefaction of air. Nitrogen is produced commercially from air by liquefaction, followed by fractional distillation. Liquid nitrogen boils off at 78 Kelvin, leaving behind liquid oxygen. The nitrogen collected as above also contains small amount of oxygen and some of the noble gases. In the laboratory, it is prepared by the reaction of aqueous ammonium chloride here and sodium nitrate. According to this reaction, which evolves nitrogen gas. Properties of nitrogen. Physical properties. Nitrogen is a colorless, odorless, tasteless gas. It is non-toxic. It has a very low solubility in water at 23.2 centimeters cubes per liter of water at 0 degrees Celsius and 1 atmosphere. Its melting and boiling points are 63.2 and 77.2 Kelvin, and it is absorbed by charcoal. Chemical properties of nitrogen. Nitrogen is rather chemically non-reactive at ordinary temperatures. It's neither combustible nor a supporter of combustion. The bond in the nitrogen-nitrogen diatomic molecule is triple bond character with a bond distance of 109.8 picometers, and it is very stable, one of the strongest bonds with a bond dissociation energy of 946 kilojoules per mole. At higher temperatures, nitrogen combines with metals and nonmetals to form ionic and covalent nitrides, as shown by the examples below. Here's a reaction with magnesium or lithium to form an ionic compound, or with hydrogen or oxygen to form covalent compounds. It reacts with carbon to form calcium carbide, giving calcium cyanamide used in agriculture as fertilizer, shown here. The main use of nitrogen is in the manufacture of ammonia and other industrial nitrogen chemicals, such as nitric acid and calcium cyanamide. It is used as an inert gas in the steel industry, where a diluting gas, diluent, is needed for reactive chemicals. Liquid nitrogen is used as a refrigerant to preserve biological materials, food, and in cryosurgery. Natural fixation is when large amounts of nitrogen are brought into the soil, either by lightning or by organisms such as algae or symbiotic bacteria. The oxides formed are then converted to nitrates by rain and then function as fertilizers in the soil. Artificial fixation is when large amounts of nitrogen are converted to ammonia by the Haber process and then to other compounds. Ammonia and ammonia compounds. Ammonia is manufactured by the Haber process. It involves direct combination of nitrogen and hydrogen to produce this ammonia. The reaction is a reversible exothermic process leading to a decreasing in volume of the gases. Low temperature, high pressure, and a catalyst are suitable for the production of maximum amount of ammonia in this process. The process uses a finely divided iron catalyst and a molybdenum promoter for maximum yield of ammonia. The ammonia formed and collected is then liquefied and stored. The unreacted gases will be recirculated back into the chamber. Ammonia is highly soluble in water, and the aqueous solution is basic due to the formation of hydroxide ions, as demonstrated in the reaction below, between ammonia and liquid water. Being basic, it neutralizes acids to their corresponding salts, known as ammonium salts. The reactions below give 2 examples of salts formed from ammonia and an acid. Ammonia and hydrochloric acid to produce ammonium chloride, ammonium hydroxide and sulfuric acid to produce ammonium sulfate and water. When reacted with heavy metal salt solutions, it forms ammonium chloride and the solid metal hydroxides. The reactions below give 3 examples, reacting with these metal salt solutions of iron, aluminum, and chromium chloride. That ammonium will form metal hydroxide precipitates. You can see the metal hydroxide solid precipitates, and is useful for the identification of these metals in qualitative analysis. So if it's brown solid, it's often indicative of iron, white aluminum, and green chromium. Ammonia reacts with halogens to form the respective ammonium halides according to the reactions below. So you can see if I react with chlorine and excess ammonia, I get ammonium chloride and nitrogen gas. If instead I have an excess of chlorine, I get ammonia and HCl. With bromine, I get ammonium bromide and nitrogen gas. And with iodide, I get ammonium Ni3, nitrogen triiodide ammoniate, which is a mild shock-sensitive explosive, along with HI. Ammonium nitrate, ammonium sulfate, and ammonium phosphate are used widely as fertilizers. Nitrogen oxides. Nitrogen forms a number of oxides in which the oxidation state of nitrogen ranges from +1 to +5. Some examples are shown in the table below. So you can see various nitrogen oxides: nitrous oxide, nitric oxide, dinitrogen trioxide, nitrogen dioxide, dinitrogen tetroxide, and dinitrogen pentoxide, with the corresponding oxidation state and physical state. Nitrous oxide, N2O, is prepared by heating ammonium nitrate, as shown here. So we heat this compound, we get nitrous oxide and water. Nitrous oxide is also known as laughing gas, as it causes hysterical laughter. In small amounts, it acts as an anesthetic agent. The main use of this oxide is as a propellant in whipped ice cream. Nitrogen dioxide, NO2, is prepared by heating nitrates of heavy metals, such as lead nitrate. So if I heat this lead nitrate, I get lead 2 oxide, nitrogen dioxide, and oxygen gas. It can also be prepared by the action of nitric acid on metals like copper, silver, and lead. So copper, silver, lead in the presence of this nitric acid, will produce a copper nitrate solution, water, and nitrogen dioxide. Nitrogen dioxide, NO2, exists in equilibrium with its dimer, N2O4, as shown in the equation below. The reaction is exothermic. As a result, the amount of N2O4 present increases at lower temperatures. The main use of nitrogen dioxide is in the manufacture of nitric acid and nitrate fertilizers. N2O4 is used as an oxidizer for rocket fuels in missiles and space vehicles. Nitric acid, HNO3, is the most stable and important oxyacid of nitrogen. Nitric acid is important to industry for a variety of uses. It is manufactured by the catalytic oxidation of ammonia, known as the Ostwald process. The ammonia required for this is obtained from the Haber's process. Ammonia is mixed with dust-free air in a 1:10 ratio by volume. The mixture is passed through a converter packed with steel and platinum rhodium gauze as a catalyst. The converter is heated to 1100 Kelvin and the ammonia is oxidized to nitric oxide, NO. The exothermic reaction will maintain the temperature and further heating is not required. About 90 to 95% of the ammonia is oxidized to NO. The mixture of gases coming out of the converter catalyst chamber is then cooled to 325 Kelvin with the help of cooling pipes and heat exchangers. The cooled gas mixture is then treated in the oxidation chamber, where it is mixed with more air and is oxidized to nitrogen dioxide. The nitrogen dioxide is then introduced into an absorption chamber packed with flint quartz pieces. Water is sprayed from the top of the tower. Nitrogen dioxide dissolves in water in the presence of air to produce dilute nitric acid as shown. The dilute nitric acid is concentrated by distillation under reduced pressure and dehydration with concentrated H2SO4. Fuming nitric acid is obtained by dissolving excess NO2 in the concentrated HNO3. Laboratory preparation. In the lab, nitric acid is prepared by heating sodium nitrate or potassium nitrate with concentrated H2SO4 at 450 to 475 Kelvin in a glass retort. Anhydrous nitric acid is obtained by distillation of concentrated HNO3 with P4O10. Pure nitric acid is a colorless, fuming liquid with pungent odor. A 68.5% nitric acid solution forms an azeotrope with water. An azeotrope is a mixture of liquids that maintains a constant composition and boiling point throughout distillation. Nitric acid is very corrosive, and on skin it produces painful blisters. It boils at 355.6 Kelvin and freezes to a white solid at 231.4 Kelvin. Concentrated nitric acid is a good oxidizing agent. Nitric acid reacts with all metals with few exceptions, forming a variety of products. Noble metals like gold and platinum have no reaction with nitric acid, but they dissolve in aqua regia, a 3-to-1 mixture of HCl and HNO3 mixture, forming nitrosyl chloride and nitrogen dioxide, NO2. Passivity of a metal is when a metal is made unreactive. When dipped in concentrated HNO3, some metals like nickel, iron, and aluminum lose their normal activity and become passive. The passivity is due to the formation of a thin protective layer of metal oxide on the surface of the metal, which prevents further action. Nitric acid is used for the nitration of several organic compounds. One example is the formation of the explosive trinitroglycerin, TNT, the substance used for making dynamite. Nitric acid reacts with proteins to form a yellow compound called xanthoprotein. The formation of xanthoprotein is the reason the skin color changes to yellow when it comes in contact with skin. Another important use of nitric acid is in the manufacture of ammonium nitrate and basic calcium nitrate, which are used as fertilizers. It is used in the preparation of perfumes, dyes, and medicines, and also used for manufacture of artificial silk. Nitric acid is used for the purification of gold and silver and widely used as a laboratory reagent. In qualitative analysis, the presence of nitrate is identified by the ring test. A ring test is conducted by adding sulfate to a nitrate solution, forming a brown ring.